vector functions. So recall, we're just looking at now the geometric equations of curves. So in 2D, it's going to be a curve. And that's only one parameter. Okay. So in 2D, let's say we have what? We have x equal to cosine t and y equals to sine t. And let's say we have a range of our parameter t to be between 0 and pi. Okay. So if you think about this, okay, x equals cosine, y equals to sine, that's definitely on the unit circle. And then here t is half a period. So basically it's always when we talk about the trajectory of this kind of a point, cosine and sine, it's always on the unit circle. But now we just go from the 0 rotation angle to pi, right? Which is counterclockwise. So that's actually a semicircle. So basically, here, when we have t equals 0, we're at this point. When we have t equals pi, we're at this point. And for whatever point that we have, it's actually, let's say, this is the rotation angle t. Right? So when this is the rotation angle t, and our radius of the semicircle is 1, right? And so basically, this is actually the curve, and if you travel, it will be this path, right? From the left, from the right to the left, is counterclockwise. Upper half. This is the upper half of a circle. Okay, circle. Okay. And for whatever red point right here, this is the point cosine t sine t. Right. So that t is exactly the counterclockwise rotation angle, starting from the direction of the x-axis. You're just moving along this semicircle. Okay. So now if you think about it, basically you have a parameter t from 0 to pi, and you have defined a point along this curve in red. Okay, and another way to think about it is that this also defines you the head of a vector starting at the origin. Right? So that's something different. But in either case, we have what? We have input as parameter t, and we have some calculation method, which is our vector function. And eventually we have two coordinates, x and y. Okay? And in our situation here, x is computed by cosine of t, y is computed. So this is what's called a vector function. So you input a parameter and you output a vector. Okay? But this is a two-dimensional case. And actually, we have seen something in 3D already. So for parametric equation in R3, we have seen that's a line, right? Equation of the line, parametric equation of the line. So x, let's say, equal to y minus t, y equals to 1 plus t, z equals to 2t. But here, so when your t is just free, when there's no range of this parameter, then this is exactly the line, right? Going through the point 1, 1, 0, and have along the direction negative t, negative 1, 1, 2, right? But now let's say we put a range so that t is between 0 and 1. Okay. So what does this give you? So basically, in the three-dimensional space, so we just mentioned that it goes through the point 110. That's actually right here. Okay. And this is also exactly the point that you get when t is just 0, right? So now we can think about the destination where t is 1. So if you make t equal to 1, you will have a 0, 2, 2. 0 to 2 is actually right here. Okay. So we do have a starting point and an end point. So in this situation, if you ignore the range of t, it's going to be the gray. It's going to be the entire line. Let me think about it. So yeah, I'm going to put it in black. So I'm going to put this in black. So this is the line that has the parametric equation in black. Okay. But now if we think about the parameter from 0 to t, exactly we are looking at the way that you travel from the bottom point to the top point. Okay. Which is a line segment. But this is what happens if you make t between 0 and 1.
May I please touch the point?
Oh. Thanks for reminding me. So t goes from 0 to 1. We are actually at the part of the line. Okay. And then in this case, we have the input t as the parameter, but now we have the way that we define the vector function. And we are outputting a vector of 3 components, x, y, z. So that's kind of a real generalized curve. That's in 3D. So now we can imagine that in general, we just need 3 components. Okay? So components of x, components of y, components of z. And as long as we define the 3 components as possibly 3 different univariate functions, then that's representing a curve. Okay? Representing a curve R3. So when we write a vector function, it's just going to be called R. And then basically it's going to be in angled brackets of f of t, g of t, and h of t. So we have 3 component functions in the variable t, and also you can write it as f of t I plus g of t j plus h of t j. So the function here, the function R. So now if you think about the R, so basically we have a domain that's in terms of t. Okay, there's only one variable that's from R to R3. Okay. So one parameter to a vector of 3 components. This is called a vector function. Functions f of t, g of t, h of t are called component functions. There are 3 components, so we have 3 functions. So in general, it doesn't have to be that line. so it could be much more general. So this curve could be something like really curvy, but yeah, so let's quickly do the axes. And it could be something like this. So right here, so what you can imagine is that it's some kind of a curve, but it will cross itself in a certain way. So it doesn't have. So here, what I have illustrated is that it doesn't have to cross itself, but it can go behind the curve that's right in front of you. So there's a piece at the front, and then there's a piece at the rear side. Okay? So it can travel like this. So this is the kind of a curve that you are just using the round component expression. Okay? But if you just stick to something like this, where you just use a vector form, then essentially you are looking at basically a vector function like this. Okay? So this is that R of t. So basically, at every point on the curve, we just use that point as a head of the vector. Okay? And it could be something like this if you're choosing a different t. Right? And then it could be something like that if you're just choosing another t. Okay? So this is a space curve. So let's look at a few examples. Example. Of course, that's the line 1 minus t, 1 plus t, 2t. That's a vector function. Let's look at another one, which is a little more general. But let's see. If we have the first component to be cosine of t, the second component to be sine of t, but the third component is exactly t. Okay. So let's see what happens here. So, and also we just make sure that t is always non-negative. Okay. So now, basically, this part and the x and y components, that looks familiar, right? That's actually, if you only look at the xy part, this is going to be just on the unit circle. And now we're saying t is just non-negative, so basically it will be periodically just circulating around the circle counterclockwise, right? So the period is too high here. So basically, what I'm saying is that if you make t going from 0, so it's yeah. So let me put the axis. So in terms of the xy axis, you always stay on the unit circle, but the way that you travel is counterclockwise. So it starts when t is 0, is right here, but then it will just travel along the circle periodically. Okay, so basically it's just counterclockwise, and it's rotated. However, if you now look at the last component, when when your parameter increases, your elevation of the point actually just goes larger and larger, right? So, and it relies on the parameter t linearly. Okay, so you somehow can imagine what we are seeing here is that okay, in terms of the xy components, you're just circulating. However, that red dot, at first it has an elevation of 0, and then it just gets larger and larger. So it's somehow although it's rotating right in front of your eyes, but then it's just getting closer to your face. Okay, and also it just goes beyond and it's just vertically out. Okay, so that's something you can imagine. And if we want to do illustration, what do we know? We know this is actually on the cylinder, right? So basically, x squared plus y squared equals 1 is actually a circle, and it just goes all the way up. So it's definitely on the cylinder. So that's the unit, so that's the cylinder that's formed by the unit circle. So X, Y, Z. Okay. But now, basically, what it does is that at first we are at this point equals 0. We're at the point 1, 0, 0. Right? So now, when you increase t, we are just rotating along the within the xy. If you just doing the projection down to the xy plane, it's going to be along the circle. But now the z value just increases, right? So let's say when we are at this point, right here, that's actually t equal to pi over 2, right? So basically, at pi over 2 is the parameter that you need in order to get to this side, right here. Okay. So this is where t equal to pi over 2. And the point is what? The point is 0, 1, pi over 2. Okay. But somehow, as a curve, we will just travel up here. And it just continues, right? So basically, when your t, when the parameter t increases by pi over 2, you're just counterclockwise rotating for 90 degrees. And at the same time, your height, your elevation just increased by pi over. So you will actually go to the point somewhere like right here. And then like right here. So yeah, let me make it transparent. So this is behind the scene. And just travels all the way here, and then you'll go up. Right. Somehow we can try to imagine that this is exactly one period, right? So this is where you have, and it just continues. Okay. So this is exactly 1, 0, 2 pi, right? So now you circulate for 2 pi, and then you get the original point 1, 0. But then your elevation is t, which is 2 pi, right? Right. Any questions so far? Right. So the parametric equation of a curve. So earlier we were talking about the vector function form where we just make component. So we just put everything in terms of a vector and we put the component functions in the XYZ components, right? But then if you want to do the parametric equation, that's just x equal to f of t, y equal to g of t, z equal to f of t. Okay, so where t is the parameter. So here we actually have two different, slightly different perspectives. Remark. Based on the vector function and parametric equations. We have two closely related geometric perspectives. Of space curves. So, yeah, let's basically quickly take a look at the figure that we had, right here, okay? So this purple curve is actually that, a parametric curve that we write, okay? So if you're writing the parametric curve, you just, you have a subpoint and an endpoint, right? But if you're doing the vector function, you actually represented the vector that has a hat on your curve. So this is slightly different. So let's quickly sketch it right here. So for the vector for the curve is like this. But if I want to copy it, so I'm just gonna do slightly different perspectives. So as well, I probably have to write it again. For the vector function form, we are looking at this is R of 0. Okay, so we know for the parameter t. So t when t is at 0, we have the lower point. When t is 1, we have the higher point. So which is 0 to 2. Okay, so R of 0 is, if you recall, that's 1, 1, 0, right? And now for whatever t is actually somewhere in between. Yeah, so that's our t. And now for the parametric equation, that's just traveling all the way here. So we don't really have the vector form anymore. So this is where when the t is 0. So we have the point f of 0, g of 0, h of 0. So the notation looks a little bit messy. We don't really have that nice R notation anymore, but the point is still going to be the same point. Okay. When t is 1, we just have the point f of 1, g of 1, h of 1, and that's 0 to 2. Okay. So the difference here is that one is that you are using angle brackets for the vector function and round brackets for the parametric curve, and the notation is a bit different. Okay. So this is the vector function on the left hand side, and the parametric equation on the right hand side. Right. So that's the starting point of these the entire chapter. But then once we realize that we just have a single parameter t, and we have 3 component functions, they are univariate, and then we can start talking about the continuity of the curve. We can talk about the derivatives component wise, and anti-derivatives and integration component wise. Okay, so we're going to quickly do that. So what's a continuous curve? So that's highly related to our definition of the continuous function for a univariate in a univariate case. Okay, so in a univariate case, in a way, you can say, okay, the graph of the function is continuous. Basically, everything is connected, right? And then in a space curve is roughly the same idea. So if you think about it, every component, F, G, and H, they're continuous, right? So the whole thing is continuous. So that's continuous space. But then suppose there's a kind of a jump, right? So in the univariate case, if your graph of a function has a jump, there's this open circle and the closed circle, they are not at the same location. Right? And then that's definitely not continuous. Okay. So not continuous. So this is the same idea. And for the definition, we call function, let's say g of t is continuous. If you recall, we firstly defined the continuity at a point, and then we extend it to the entire domain. Right? So when t is a, if at t equal to a is continuous, that just means the limit when our parameter t approaches a of the function exactly equals to the functional value at the point a. Okay. So if you think about it, there are two side limits, right? So when t is approaching a from the left, when t is approaching a from the right, the two limits have to exist and they have to agree with the functional value. So a few more pictures. Somehow you can recall that if your function is let's say going up like right here, and then all of a sudden it just functional value just jump to an open circle like right here, this is definitely not continuous. Okay. So if you think about this a g of a, this is the solid dot. This tells you the functional value at the input a. But then the left-hand limit tells you, okay, I'm approaching this functional value. However, the right-hand limit tells me I'm approaching another value right here. Okay, so there's definitely a jump. So in this situation, that's the case where function g is not continuous at a point. And of course, when you talk about continuity, even though the curve can be sharp, but still it's continuous. Okay? So the definition is really about whether everything is sort of connected or not. Okay? So if you think about g of t equals to the absolute value of t, let's say. So on the right hand side, the slope looks looks to be 1. The left hand side, the slope looks to be -1. But if you approach 0, then you see the functional value just agrees. But well, the left hand limit is 0, the right hand limit is 0, and the functional value is also 0. Okay. So this in this case, g is continuous at equal to 0. Okay. So just like a quick review of the limit of a univariate function. Okay. So the left hand limit, right hand limit, and the functional value, 3 things they have to agree. Okay. And in terms of a vector function, it's the same idea. We just need the 3 components to be continuous. Then the whole thing is continuous. If any component is not continuous, then no. Okay. It's not going to be a continuous group. So if R of t equals to the vector function having components L of t, G of t, H of t, then the limit when t approaches a of the entire vector function is just going to be defined as the component-wise limit. Okay, so we just take the limit where of every component respectively. FGH. Of course, when we are taking it component-wise, we don't want to switch the coordinates. Right? So yeah, that's the definition here. A vector function R t is continuous at t equals a if the limit at the point A equals to the functional value at the point. Okay. Vector functional value at the point. Okay, so just a direct extension from multivariate calculus. Quick example. Let's look at the vector function of t, which equals to this piecewise defined. So it's 1 plus t cubed I plus t e to negative t j plus sine of t over t. Okay. When t is non-zero. So you see, okay, the only thing that's illegal here is the denominator t, right? So when t is 0, it's not legal. So when t is 0, we are going to define the vector function as I plus k. So here is our t continuous at equal to 0. Here we just need to take the limits. The limits when t goes to 0 of our t. So we just take the limits component wise. So the limits when t goes to 0 of 1 plus t to the 3. So that's definitely 1, right? There's so you just plug in t equals to 0 and see what it gets you. So that's gonna be a 1. And then the limit when t goes to 0 of t e to the negative t. So you can try plugging in 0. So it's gonna be 0 times e to the negative 0, which is 0 times 1. That's a 0. Right? The last component we use is calculation if you are not familiar with the limits. Okay, so but it should be really standard if you have seen it, because this is just a Laplace rule. So sine of t over t, the limit when t goes to 0 is actually going to give you 1. So now if you look at this in the component expression is 1, 0, 1. If you want to write it in the standard basis, it's going to be I plus k. Okay, so that agrees with our R0. So to quickly write down the conclusion, we know, okay, the limit equals to the function value. So Rt is continuous at t equals 0. Okay. That's the conclusion. And of course, if you want to be reminded about the limit calculation here, recall when t goes to 0, the limit of sine of t over t, let's see how we will apply the Laplace rule. So firstly, try plugging in 0 in the numerator and denominator. So sine of 0 is 0. And the bottom, the denominator is also 0. So it's the 0 over 0 type, which is undetermined. Okay. So this is something you should have in your mind. So you have 0, 0 type, what do? So you need to apply the Laplace rule, basically take the derivative of the top and bottom. So that the limits, the resulting limit will still stay the same value. So this equals to the limit when t equals to 0 of the derivatives dividing. Okay, so the derivative of the top is cosine. The derivative of cosine, the derivative of t is 1. Okay. So now let's plug in t equal to 0 again. So that will give us cosine of 0, which is 1. And then we're done.